Reaction mechanism is the last thing we'll be looking at for this section. Looking at basically the mechanisms that drive a reaction, a more complicated reaction. How exactly does it happen? Now, to start talking about this, I have a really, really good example, a really good analogy. We can think of reaction mechanisms as a process of doing dishes, quote unquote. The process of doing dishes is more than just one step. There, we can look at this funky diagram I have here. So we have this crew over here. They're clearing the table. Not playing poker, but clearing the table off the dishes. Then we have this, so then that, of course, leads to this person here. This is the dishwashing area. And of course, that leads to, assuming washing and drying, so I didn't draw any drawing. And then I have these guys over here putting dishes away on some weird shelf. Okay? So as we can see here, there's a three-step process. The process of doing dishes can be thought of as three different things. And by looking at this, you can tell that, you know what? This is the weakest link right here. Because here I have two people clearing the table, one person washing the dishes, three people putting dishes away. This washing dishes part is the weakest link. It's the slowest step, therefore it will determine the rate of the overall reaction. Eventually what will happen is that dishes will start to pile up. These guys over here will be waiting for dishes, and I could add more people here, it won't affect anything. If I could add more people there, it won't affect anything. I would have to add more people to the rate determining step in order to speed up the reaction. So, looking at, from a chemistry point of view, reactions involving more than two reactants are broken down into elementary steps as well. So, doing dishes, broken down into steps. A reaction involving more than two things are broken down into a series of steps too. Because you have to think about it. For a successful reaction, molecules have to hit in the right way with enough energy. So if you had more than two reactants, they'd have to all come together at the right way with the right energy. Extremely difficult for more than two reactants to do that. And this is an example that I believe is in the textbook. So we can think of this, a reaction like this. Two molecules of nitrogen monoxide combined with two molecules of hydrogen, producing one molecule of nitrogen and two molecules of water. So here we're implying that 2 and 2, a total of 4 molecules come together in the right way with the right energy to overcome the activation energy. As the old expression goes, the chances of that happening are slim to none, and Slim just left town. So this complex reaction is believed to occur in a series of steps and have the following reaction mechanism through which it's believed to occur. So if we take a look here, 3 steps we can think of this as. So first of all, we have the 2 NOs forming N2O2. That's a relatively fast reaction. Then that N2O2 molecule combines with a hydrogen to form N2O and water. And then that last N2O combines with the last hydrogen and form this. And we're told that this middle step is the rate determining one. It's the slowest one, whereas the other ones are fairly quick. Now we can do a couple of things here. These products that are then used as reactants in the next step, those are termed intermediates. And we can simply cross them off because they're produced and then used up. They won't appear. And notice you don't see that molecule up there. There's another one, N2O and N2O. It also is produced and then used up in the next step. So we can cross it off, and you'll notice that we're left with 2 NOs plus 2 hydrogens, a nitrogen, and 2 molecules of water. And that, in fact, is the reaction that we had up here. It's identical, 2NO plus 2H2 plus N2 plus 2H2O. So that overall reaction can be summed up as a process of those steps right there. Okay? And of course we could draw a reaction energy versus progress diagram again. We'll take a look and see a couple of things about it. So energy versus progress. You see 3 distinctive loops there corresponding to the 3 distinctive reactions. So reaction 1, reaction 2, reaction 3, and you'll notice that this middle step is the highest. And of course that corresponds to the slowest step. And chances are it's slower than the rest of them because it has a higher energy requirement. So it takes more energy to get through that second reaction, so we show that as a large loop on the graph there. Whereas the other ones they're lower, it doesn't matter where they are, it's just that they are lower than that one, so you can definitely see that one's higher than the other. So the rate determining one, the other one, 3 loops. One other thing we could look at here, here's where the reactants are, here's where the products are, and of course one final thing here, we have high energy reactants. They go through this whole process, make lower energy products, so of course the enthalpy of that reaction is going to be negative. So it, in fact, is overall an exothermic reaction. So there we have it, reaction mechanism.